www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Hello, my name is Arijit Ray Chaudhary, and today I'll make a brief presentation about the tool that we have developed here in Purdue. It's called PETE. The title of my talk would be Simulating with PETE, which is the Purdue Exploratory Technology Evaluator. And I would like to acknowledge Charles and Yunfei, who has worked with me, and also contributions by Professor Mark Landstrom and Professor Kaushik Roy in development of this tool. Before I start on the flow of the tool itself, let me spend a couple of minutes on the motivation behind this tool. So if I look at the typical system and circuit design environment in the digital VLSI area, on the far extreme end we have this physics and materials section, and there is this device design, and there is a close interaction that goes on between the physics and the materials and the device design. However, once the device is finalized, which is the MOSFET that we use these days, once this is finalized, it goes to the circuit designer as kind of a black box, and the circuit designer can use the IV and the capacitance and all the design rules that the device designer and the technology people would provide to them, and then work with the system and the architect, system architect designers in order to get the best performing system with the lowest possible power. So if I look at this curve or this flow chart, essentially there is a gap between the device design and the circuit design. Although there is a close interaction between physics and the device design, there is hardly an interaction that goes on between the circuit and the device. But as we come up with new and new devices in this nanotechnology area, it's important somehow to bridge this gap so that device designers and materials scientists and physicists can, at the point of inception of a new device, figure out what is the circuit and system level performance and power of this new device that they are evaluating. So with that in mind, we wanted to bridge this gap so that we can provide a tool to device designers and material scientists and physicists, so that once they come up with a new device with a promising IV and CV characteristic, they can figure out very easily what would be a system and architecture level significance of this device if they were to use it in a CMOS-like environment. So we are essentially looking at devices which can be used as drop-in replacements of the traditional CMOS transistor, and the tool that we have developed can provide feedback to the device designers and physicists about the system and architecture level power performance trade-off with this new device. So the idea is to have a quick and approximate, or we cannot guarantee 100% accuracy, of course. So the idea is to provide a quick and an approximate evaluation of any new device, and it needs to be done from a circuit and architecture perspective, and it has to be done very quickly, and this feedback has to be provided back to the device designers. So this is a brief overview of my talk. Initially, I'll talk about the tool that we have developed. It's called PETE. I'll talk about the different kinds of input methods to the tool. I'll talk about a MOSFET model and a table-based input which can be provided to the tool. Then I'll briefly talk about algorithms for estimating delay and power by this tool that we have used, and finally present some results and comparisons. At the end, I'll make a brief demonstration of how data can be how one can import data into this tool, and also show some screenshots of the tool that we have in NanoHub. And finally, I'll draw some conclusions and summary. So first, let's look at the input to the tool. We'll talk about a MOSFET kind of model and a table-based input model. So the tool that we have can essentially work with two kinds of data input. One is a MOSFET-like device that we have, which is characterized by a subthreshold slope, a VT, and R-on, and a mobility, and several other parameters, which we believe can efficiently efficiently capture the essence of any MOSFET-like device. And then we will develop a set of cell libraries with these devices, which are the basic elements for developing a digital circuit and a system. And then we will evaluate some benchmark circuits with these cell libraries. On the other side, we can also look at any arbitrary device where some experimentalist or someone who is working in device simulation area has come up with an IV characteristic and a CV characteristic. And our idea is to get this new device and try and figure out what would be a system and circuit level performance for this device. So we can similarly develop the cell libraries for this device, characterize the cell libraries for delay and power and leakage, and then evaluate some benchmark circuits. So these are two different ways in which the tool can at this moment evaluate any new device technology. So first let's look at the MOSFET model and how we can handle the MOSFET model in this tool. So the idea is to have MOSFET-like devices which are characterized by a set of parameters like the subthreshold slope, the threshold voltage, dibble, the factor M, which is essentially 1 plus the ratio of the oxide capacitor and the semiconducting capacitor, and then factors like mobility, which determines the on current of the device. And the cell library that we have at the moment consists of 4 basic gates: the NAND gate, the NOR gate, both of which are 2 input gates, then an XOR gate and an inverter. So this is the primitive cell library that we are working with. So if I look at the algorithmic flow of the input to this tool, let's look at the flow chart from the left hand corner. So we want to generate the IV and the CV tables from MOSFET parameters. So what we do is we provide all these different parameters which can characterize a MOSFET, and from those we can have very simple minded equations in order to get an IV and the CV characteristics of the new device. So once we get this IV and the CV in terms of tables, we can import it directly to the tool PETE. On the other hand, we can also read the IV and the CV data directly from the user, and this IV and CV data, which is shown on the top right hand box, can come from either, let's say, an experiment, or it can come from a device simulator. So once we have the IV and the CV data, does not matter whether it has come from a MOSFET model or whether it has come from an experiment, we can construct an IV and a CV table with the proper resolution and with a proper uniform grid, which can essentially be used in this simulation tool. Just to give you an idea of what kind of MOSFET model we are using in PETE, I have a set of current voltage equations which show the dependence of IDS, or the drain current, on the VGS and the VDS in our model. In the subthreshold region of operation, we assume an exponential relationship which is characterized by the subthreshold slope S and also the off current of the device. In the superthreshold region, we assume velocity saturation of the device, and the equation here essentially shows that we take a velocity saturated MOSFET with a lambda parameter, which gives us the early effect in this kind of MOSFET devices. Finally, once we have constructed the IV and the CV tables with the proper resolution and in a uniform grid, we perform a bunch of checks. For example, the polarity checks, the VDD ranges that the user has provided as input, and also a bunch of other checks which can generate potential errors and warnings. So this part of the tool is important because we are essentially looking at IV and CV characteristics which can come from experiments and other device simulation tools. And we wanted to make sure that before we go further into actually simulating these devices for any new circuits or system, we wanted to make sure that the data has been provided in the correct format and all the correct data is provided, so that the tool can actually give a reasonable estimate and not give any false estimate of the performance of these devices. In the next slide, I am showing what a table-based input would look like in this tool. So one of the characteristics of this tool is it can handle numerical table-based IV and CV data. So this is an important feature of the tool, because in general, if I have a new device and want to estimate the circuit or system level performance of the device, it is essential to develop a compact model so that we can run SPICE kind of simulations or circuit simulations on this device. But with nanotechnology coming, with nanotechnology and all these new devices that are being thought of at a very fast rate, it is not always possible to come up with new compact models, because the development cycle of a compact model is quite long. So we wanted to make sure that we provide some kind of a workbench or some kind of a quick simulation environment by which our user can provide numerical values of IV and CV and get a good estimate of the circuit and circuit level performance and power. So if I look at a MOSFET, I have so the two important data sets that have to be provided to the tool would be IDS and the C gate, or the gate input capacitance. So the IDS is a function of VDS as well as VGS, and this has been shown in the bottom left hand corner of the slide, where we have a 2D matrix where ID has been provided as a 2D matrix, and ID is a function of both VG, which is the gate voltage, and as well as VD, which is the drain voltage. On the right hand side of the slide, we have the gate input capacitance. And when we say gate input capacitance, we are essentially looking at the MOSFET C capacitance, or MOS C capacitance, which is obtained by shorting the drain and the source and providing a bias to gate and measuring the gate input capacitance. Of course, this gate input capacitance will not be a constant. It is a nonlinear capacitor, and it will vary with the gate voltage. So for the capacitance, I have a 1D array where we have the gate input capacitance varying with the gate voltage, and this will be a nonlinear capacitor that we are trying to model. So the tool PETE will essentially require two sets of data. One is a 2D matrix of current, and one 1D array of C gate, or gate input capacitance. And I'll show in later in my presentation how these two can be provided in the simulation environment. Till so far, I have talked about what the gate input capacitance would be, and in the next slide I am looking at an inverter driving an inverter, which is one of the fundamental logic scenarios or logic gates that we are looking at. The gate input capacitance would consist of the PMOS capacitance as well as the NMOS capacitance, which are nonlinear and obtained by doing the MOS-C simulation of these transistors. But apart from that, we all know that a circuit and system level evaluation should always incorporate all the necessary parasitics that come with the design. So if I look at the parasitics should be lumped together, and we are assuming that the parasitics can be lumped together and provided as a lumped parasitic between at the output node of any cell or any gate. So the total load capacitance that the inverter would see would essentially be the C gate, which is the gate input capacitance of the next logic stage, plus some other capacitors, which are essentially the parasitic capacitors. In our present simulation environment, we have captured two kinds of parasitic capacitors. The first one, let's look at what are the device parasitic capacitors that one can typically get in a MOSFET. So on the right hand side, I am showing a typical schematic of a MOSFET with all the different parasitic capacitors, and these parasitic capacitors, if I may point out, are all dependent on the width of the device. So this part of the capacitor can be looked at as the device parasitic capacitor, and they are width dependent, meaning that as all these parasitic capacitors will scale as a function of W, or width of the device. Apart from that, we have another capacitor which does not scale with the width of the device. This capacitor is essentially the capacitor of the interconnect when one wants to join one cell with another. So in the figure on the bottom, I am showing a typical layout where this yellow line, which has been circled, shows an interconnect which links one of the cells on the left with one of the cells on the right. So this interconnect will also provide some capacitor, which will be another parasitic capacitor we need to consider, and this capacitor would not scale with the width of these devices. So if I put all these parasitics together, what we are essentially looking at is a total load capacitance which is equal to the gate capacitance and a parasitic device capacitance, and another parasitic capacitance which I call the intercell capacitance or the interconnect capacitance, and this is width independent. So we have two kinds of parasitic capacitors that we wanted to capture in PETE. One is a width dependent capacitor, the other is the width independent capacitor. And in order to do a technology evaluation of any new device, the user must provide a reasonably good estimate of both the width dependent capacitor as well as the width independent capacitor. Next, we will talk briefly about the algorithms for estimating delay and power in this simulation environment. In the next slide, I am showing the different kinds of output that the tool would provide. On the left, I have the DC characteristics. So once the user provides the IV or the CV data or the MOSFET input parameters, the first task that he or she can perform is to get a DC characteristic of the new device. By DC characteristic is meant the voltage transfer characteristic of an inverter with all the necessary information that the voltage transfer characteristic can provide. This is done simply by equating the PMOS and the NMOS currents for different input voltages, and we get the output voltage. So this is a numerical solver that we have written in order to get the VTC as a function of the output voltage as a function of the input voltage. And once we obtain the VTC or the voltage transfer characteristic, we can very easily obtain other important parameters which are very textbook parameters, which are VOL, which is output low voltage, VOH, which is output high voltage, as well as input low, input high voltages. And finally, as an output of the tool, we will draw the VTC, and it will show the gain and as well as all the noise margins in the for that particular inverter. Once the DC characteristic evaluation has been performed, it is prudent to go and do a transient characteristic analysis as well. One of the major differences between a traditional circuit simulator and the tool that we have developed is that we wanted to make all these estimations of delay and power in a very quick and short time. So we have done this simulation not in the time domain but rather in the voltage domain. So in a time domain environment like in SPICE, essentially in a SPICE-like environment, one would try to solve the voltages at all different nodes of a circuit at a particular instance of time, and then would increase the time by a step of delta t, let's say, and evaluate again the voltages and currents at different nodes. So this is a time-based simulation that any traditional circuit tool would perform. But that essentially takes a long time, because in some cases we are looking at capacitors which are very large and currents which are very small. So since we do not know what kind of inputs we have to this tool, we wanted to make sure that we can always do a reasonable as well as fast estimate of delay and power. So instead of doing the simulation in the time domain, we resorted to doing it in the voltage domain. By that is meant that we divide the voltage grid from 0 to VDD into n different number of points. So whenever we have an RC circuit with the capacitor being discharged or charged through a resistive circuit, for example a PMOS charging the output load or an NMOS discharging the output load, we can evaluate the time delta t as the difference of charge between these two voltage points divided by the average of the current that flows in this voltage range. So delta t is given by Ci plus 1 Vi plus 1, which is the charge at point I plus 1 minus the charge at point I divided by the average of the current that flows in this voltage range. And the I would have to be the net current, which is the net discharging minus charging current if we are looking at discharging the output node. So if I have a capacitor, an inverter driving a capacitor, we should have the NMOS discharging the capacitor and at the same time the PMOS charging the capacitor. So we should essentially be looking at the differential current, which is the difference of current between the NMOS and the PMOS, and that is exactly what we provide in the simulation environment. And in this way it can actually give you a good estimate of the influence of off current or the offset current on the delay characteristics of typical cells. And finally, the delay we calculate is a summation of the total delays as the Vi or the input voltage changes as the input changes from 0 to 90% of the VDD. So we are looking at essentially at 90% time for the output to switch from 0 to VDD, or 90% of the time for the output to switch from VDD to 0. So this is in essence the algorithm for the transient simulation with this tool. The next important thing that one has to think about is how to simulate stacks. So let's say I have a stack of transistors which are essentially series connected transistors, and the idea is to find out what this intermediate node voltages V1, V2 up to Vn are. And the important constraint here is that the current has to be continuous. So we have to solve for current continuity and at the same time figure out what these different voltage levels are so that we can solve KCL efficiently at all these different nodes. So we have an algorithm for solving this current through a stack. So first we start with Newton-Raphson method, which is a differential based method. So using Newton-Raphson we try to figure out whether we can solve KCL self-consistently at each node. By self-consistency I mean that the KCL has to be solved such that the entire current through the stack remains constant or continuous. The Newton-Raphson method works well as long as the current voltage characteristics have good differentials and they are well behaved. So we look at whether the Jacobians for this current voltage characteristics are discontinuous or non-derivable. If they are discontinuous, then Newton-Raphson methods do not work very well. So then we can use a non-derivative based method for convergence. So if the Jacobians are discontinuous, what we use is a bisection method, and that's what I'm showing in the next slide. We use we look for some checks when we use the Newton-Raphson method. If the derivative based method produces non-convergence, for example, if we get NaNs which are not a number, or if I find that the Vn, that is the voltage at nth node, has converged to a value greater than VDD, which means that there has been non-convergence in the stack, or if any node voltage Vn plus 1 is greater than or equal to Vn, which is again a violation of the basic KVL law, then we say that there is non-convergence in the stack. In that case, we used a bisection based method for all the nodes self-consistently, so that we want to make sure that from one iteration to the next we have less than 5% or 1% of VDD of error. So this is the voltage tolerance error that we have provided in this tool. So in essence, we first try to use Newton-Raphson or a derivative based method to get to solve the current through a stack, and if we find that the derivatives of current or the Jacobians of current are not differentiable and they are not well behaved, then we use a bisection based method which can guarantee us convergence, but at the same time it will take more time to converge. So we have this we have the bisection based method still, because we are not sure of what kind of IV data the user would provide, and we wanted to make sure that we always get convergence even at the expense of longer time. Finally, we are looking at the cell library development. We know that the digital logic circuits are cell library based. We have NANDs, NORs, inverter, XORs, and different kinds of gates which would make up the entire system. We also know that that with modern day MOSFETs, where the off current is pretty high, and also with new kinds of MOSFET where the on-off ratios are not well behaved and it's not a perfect switch, matrices like CV over ion for delay and CVDD squared for switching energy are not accurate models. So it's important to capture the exact numerical value of delay and the exact numerical value of switching energy for cells. So we want to characterize the cell library for delay, power, as well as several input transition slopes. At the moment, the tool can handle several different cell primitives. These are inverters, NANDs, NORs, as well as XOR gates. On the left hand corner, I am showing the load capacitance on the x-axis and delay on the y-axis of several different gates. The solid lines show the results that have been obtained from this model, which is PETE, and the dashed line shows the results that has been obtained from SPICE, which is a traditional circuit solver. So we can see that the model and SPICE match each other pretty well for different values of load capacitance. It can also be noted that at very low values of load capacitance, there is a good amount of deviation between the SPICE and the models and what PETE gives us. And that is due to the reason that at very low values of load capacitance, the output capacitance of the device itself, which is a parasitic of the device itself, has not been well captured or not been well modeled when the user has provided the data. But at high values of load capacitance, we have a perfect match between SPICE and the model. Finally, we are looking at some of the bigger circuits, and the biggest circuit that we have is a full adder. It's an 8-bit ripple carry adder that we have simulated. So an user can provide the IV and CV characteristics of a NMOS and a PMOS and get switching energy, switching power, leakage power, delay of the critical path of an 8-bit ripple carry adder. And in order to find out the total switched capacitor, the average switched capacitor of a ripple carry adder, we have done a careful analysis of probability of propagation and activation at each node. So without going into the details of the calculation, I can show that essentially what we are trying to do is that at each node we are trying to figure out what is the activity, because the total switching energy would essentially be the CV square at that particular node multiplied by the activity at that node. And in order to calculate the activity at each node of the circuit, we have done a probability propagation, which is again a standard way of figuring out what is the total switched cap of a big circuit. So I want to point out that when we provide results for switching energy, switching power, as well as average power and average leakage, it is an it is a good estimate because we have incorporated the probability of switching and activity at each node. And for finding out the delay, we have identified the critical path of the circuit and figured out what is the total delay of the critical path of the circuit. So signal probabilities and activities are calculated and they are propagated to each node, and we obtain the total switched gap. And the delay is calculated by a static timing analysis of the critical path, and that gives us a reasonably good accurate model or estimate of the entire delay. Finally, the output. So what kind of outputs are we looking at? As far as the DC characteristics of the inverter are concerned, we are looking at typically VOL, VOH, VIL and VIH that I already mentioned. We also draw the VTC and we figure out other critical parameters like the gain of the circuit. For transient characteristics, we are essentially looking at three things. The first is of course the delay. We are also looking at switching energy and also the leakage power. So we are looking at both the delay and the power for a variety of different gates and cells. So the typical gates and cells that we are using are inverters, NANDs, NORs and XOR chains. We also do an inverter based ring oscillator, which is a 5-stage ring oscillator, and we figure out what is the switching energy and delay and power dissipation in the ring oscillator. We also look at an inverter driving a constant load. This would more or less represent a scenario where an inverter is trying to drive a big parasitic capacitor like a bus, and then we figure out what is the switching energy and delay. And also, if the same capacitor has to be driven instead of driving it with a single inverter, if we can size a buffer chain so that the delay is optimized in a big capacitive load, we do a sized buffer chain calculation of the constant load. And finally, we provide estimates of switching power and leakage power based on probability and switching activity propagation of an 8-bit full adder starting from the device characteristics of the NMOS and the PMOS. Now let's look at some of the results and comparisons with SPICE. On this plot here, I have shown the VTC of two devices that we have. The solid lines show the results obtained from PETE or this model, and the dotted lines show the results obtained by SPICE. So if I look at the VTC I should mention that this is a 45 nanometer technology node, and the SPICE simulations were done using the BSIM models generated from another tool on NanoHub, which is called the NanoCMOS, and we are looking at the 45 nanometer node of technology. And we provided the IV and the CV data to the tool PETE, and we can get a very good estimate and an exact match with SPICE. And the two different curves here are for two different values of the oxide thickness. One is a thin ox, which is 1.1 nanometer. The other is a thick ox, which is 1.8 nanometer. And we can show that we can clearly see that as the oxide has been scaled, the gain of the inverter has increased, and it has been captured very well in this simulation environment. On the right, I have typical output parameters that this DC characteristics would provide. One is of course the beta ratio, which is the width of the PMOS and the width of the NMOS, so that the charging and the discharging times are equal. We also have parameters like high noise margin and low noise margin that the tool provides, as well as maximum gain of the inverter, which in this case is around 4.5. We also have input high voltage, output low voltage, output high and output low, and all this will come out as a result of the DC characteristics of the tool. The next slide shows the match that this tool has with SPICE in terms of delay. So essentially, I am capturing three different kinds of circuits that we have worked with. One is of course the 5-stage ring oscillator that I mentioned. The other is the buffer chain, and finally the carry chain of a 1-bit full adder. And on the right, I have this histogram which shows that there is a good match between SPICE and PETE generated results. Of course, one has to remember that these results are only as accurate as the data that has been provided to this tool. So if one can provide a good estimate of the capacitance to this tool, it can do a very good job in finding out what is the delay and switching power, and it will be as accurate as that of SPICE. Finally, let's look at some of the demo. I wanted to just show a few screenshots of the tool and show how these different values can be provided to the tool. So what I'm looking at here is essentially the first screen that you will see once you open up this tool. So you have a DC, so on the simulation type, we can do a DC analysis, and there is a scroll down menu. You can also do a transient analysis. And here the different tabs show different kinds of simulation environments. You have to provide data to the PMOS the data of the NMOS, and as well as simulation parameters. If you go to this tab simulation parameters, you can see that there are parameters like VDD which you can choose, parasitic loads you can choose, and a set of other circuit level parameters that you can choose and provide to the tool. And as far as PMOS characteristics here are concerned, I have this bunch of characteristics which are MOSFET-like for a MOSFET-like device, things like subthreshold slope, mobility, lambda, threshold voltage, dibble, and so on and so forth. And this would essentially characterize the circuit. Next, I have the table-based input. So if on the top, if I look at the device model, it has been changed to table-based input. And let's say I have done an experiment and I have an Excel sheet of the IV characteristics and the CV characteristics. So on the Excel sheet, I have VG on the top and VDS. I have VDS on the top and VGS on the column side, and I have a 2D matrix of current. And below that, I have the MOS-C capacitance or capacitance as a function of VG, and I want to provide these inputs to the tool. So what I'll do is I'll provide the VD values in this blank space in the VD column. We will provide the VG values and the 2D matrix of current in this blank space. It's as simple as just putting these numbers in, and then similarly we do the same thing for the capacitors. And this is done for the PMOS, and similarly if you go to the next tab, you can do the same thing for the NMOS. And finally, you have to choose the right simulation parameters like VDD and parasitics and things like that, so that the entire simulation can be done. And then once you hit simulate, it will simulate with these IV characteristics. This is just to show how one of the screenshots of the output, and it shows how the VTC of a typical simulation run looks like. And if I scroll down from the results section, you can look at the parameters like VOL, VOH, and gain for this particular DC characteristics. The next slide shows again the transient analysis of two different kinds of devices which are totally different as far as the physics of operation is concerned. One is a thermal MOSFET which is working at VDD of 700 millivolts and with a very good subthreshold slope of around 70 millivolts per decade, and we can get the average delay of the inverters, energy per cycle, and all these different numbers for the inverter driving an inverter. On the right hand side, what I have is a band-to-band tunneling device which is a carbon nanotube based band-to-band tunneling device that we have just used for the simulation purpose. The thing to note here is that these kind of devices can potentially have subthreshold slopes better than 60 millivolts per decade, and we have just provided the IV data into this tool, and this shows that the tool has efficiently figured out what would be the inverter delay, energy per cycle for this new kind of devices. So we are not limited only to the traditional MOSFETs that we know of, but we can simulate any kind of new device, any 3-terminal device with IV and CV characteristics, and we can provide good estimates of delay as well as energy and as well as leakage power for any kind of device. So although the numbers may not be important here, the important thing to note here is that the tool can simulate any arbitrary IV and CV characteristic, and it will provide you with reasonable estimates of delay and power. Finally, before I conclude, I wanted to mention one of the shortcomings of the tool, and this is one area that we can potentially be working on in future and trying to, and we will try to improve this part of the tool. Essentially, the tool only has IV and IV data and CV data as input in the numerical table-based approach. Remember that the IV data is continuous, but since we are providing just data, discrete data, it may not be derivable. That is, at certain points, the derivative of IV may not be continuous. So essentially, although IV is continuous, the GM or the GDS may not be continuous, and this is exactly what we see on the left-hand side figure. On the x-axis, I have VDS, and on the y-axis, I have the normalized derivatives of current. And we see that the GDS here has some ripples as well as the derivative of GDS, which has huge amount of ripple. So essentially, all the computation that we do, which involves derivatives of current, would potentially have discontinuities or inaccuracies. This is exactly what we see when we plot, let's say, the gain on the y-axis and the V-in on the x-axis of an inverter. What we see is that although the results seem to match pretty well with the SPICE generated results, and the SPICE results are shown in the solid line, and the dotted line shows the results generated by PETE, we see that there is a good amount of numerical noise wherever there are sharp discontinuities and at the max gain point. So this is due to the fact that gain, which is essentially GM divided by GDS, has discontinuities, and this is something, and this comes up in the plot of gain versus V in. So in order to get the max gain or the average gain of these devices, we filter out the noise and we get the average of the gain in this around the switching point. And this is a part of the tool that we will work on in future and try and improve, so that we have smooth gain curves and smooth GDS and GM curves as well. Finally, back to the big picture, what we are essentially trying to do is provide some kind of feedback to the device design and the technology designers. So the device characteristics can be provided as IV and CV to the tool, which we call PETE, and without thinking about what goes on in a circuit design environment, the device designer or technology designer can very easily figure out what would be the system level and circuit level implications of this new device that he or she has. And we are looking at things like DC and AC characteristics. We're looking at gain, voltage transfer characteristics, as well as delay and energy. We are looking at both the switching energy as well as the leakage power. And then we are benchmarking it against we can benchmark it against an existing technology node, let's say 45 or 65 nanometer technology node. And the device designer can very easily figure out whether the new device is better than an existing 65 or 45 nanometer technology node, and do a apples to apples comparison. Finally, as a summary, we have developed a tool which can be used as a quick estimator for any new kind of device. Of course, it is not aimed towards 99% accuracy or higher accuracy, because that is not the main aim. And at an early point of inception, it is not possible to get 99% accuracy, because the layout rules, the design rules would not be known. So the idea is not to get very high accuracy, but to get a very reasonable number which will tell you the delay, power and switching energy of any new device. And one has to do that very fast. So we can do an estimate for the new devices for DC gain as well as power performance. And finally, we can also extend it to non-charge based systems as we go in future, as well as there is a sequential propagation of logic from one stage to another. At the moment, what this tool can provide are good estimates of delay and power in a typical CMOS design environment, where the transistors are just drop-in replacements of CMOS transistors. And this tool has already been deployed on NanoHub for public use, and there would also be a manual with this tool for the details of the models and how one can simulate new kinds of devices with this tool. Thank you. And if you have any questions, I'd be glad to answer. Thanks. Sure.
The only input is the IVs, right? You don't have all the capacitors, the parasitics. I mean, the IVs is enough.
Yeah, so the question is whether the IVs is enough. Yes, the IV is enough for doing the DC part of the characteristics, but for the AC part of the characteristic or the transient analysis, one has to provide the CV as well, which is essentially the intrinsic capacitor. And then you can play around with the parasitics. If you don't know what an exact value of the parasitic would be, you can change the value of the parasitic and see how the parasitic affects the performance and power in this for this new device. So if that is all, thank you so much.